Right, today we are gonna study about motion planning and its example. So this is an overview of motion planning which we are gonna study today. So basically motion planning is a problem of finding a robot motion from start state to a goal state that avoids obstacle in the environment, which belongs to the motion of the robot from a point where you have to go through an obstacle without avoiding any collision uh, in the obstacle and then goes to your goal. So there are multiple configurations of the robot in which you can see there is movement of the arm, there is movement of the joints in it. So there are a number of thetas, um, angles, and many other things. So during the movement of the robot, we can take the points of the movement into the space where it captures all the movement into the matrix form, which is written as m cross n, which belongs to m as column and n as rows. So the main point of motion planning is to start with an initial state of x of 0 as x start, and then we have to go to the final point where it stayed as x goal. So we have to find a time t where the movement of the robot will go from start x go x start to x go, which satisfy the momentum in which there is no collision or there is no collision of robot towards the obstacle, and it moves freely. So there are two assumptions made in this. One is that feedback controller can ensure that the plane motion is followed closely, because we cannot we cannot say that the feedback from the controller is 100% sure from the uh, motion which we have captured. And the second one is an accurate model of the robot and environment will evaluate C space, C configuration as free during motion planning. So it states that there is no such accurate model, so we have to make an assumption for it, which will evaluate into the free environment where the motion is going. So there are two types of motion planning problems. One is path planning versus motion planning, and the other one is um, a set of points in which there is rows and columns. So if the rows and number of columns are equal, which is different from where the number of columns is less than number of rows. So it gives you the motion of holonomic versus non-holonomic. And the path planning versus motion planning will give you some trajectory generations and many other things from it. So these are the two types of motion planning problems we have. So there are a number of methods from which we can solve the question. So here are the six methods we can use to solve an example. First is complete method, in which there is an exact representation of the geometry of the problem and the space. The second one is grid method. Discretize C space, means C free space configuration, and search the grid from Q start to the goal. So we are going to use one of the methods from this. And the third method is sampling method, which we need to take a randomly sample from C space, where we have to evaluate the X free and add new samples which we have to compare it with the previous ones. The fourth one is virtual potential fields, which will create a forces on the robot which will pull towards the goal and away from the obstacle. So it's kind of a difficult task to do it, and it's basically we have to take the robot away from the obstacle and move the robot from starting point to the goal point while creating the forces in it. So the fifth is nonlinear optimization. This is minimize some cost subjects to constraints on the controls, obstacles, and goals. So in this method, where we have to set some constraints in it to control for the controllers and obstacle to move the robot from one x start to x goal, in where we have to minimize the cost of the sensors and all the stuff to um, optimize and then um, get the motion planning out of it. And the last one is smoothing, which is giving some gases or the motion planning output improves the smoothness while avoiding the collision. So it basically gives you a smoother collision than the other, avoiding the smoother collision and gives you a proper momentum of the robot from X start to X go. So this is a configuration space obstacle in which you can see that there are two partitions of C space, which is one is C free and one is C obstacle. So what does it stand for? C free is basically momentum of robot from into the free environment, and which is integrated with the C obstacle, in which the robot is moving into an environment with some obstacles in it, and there is no there are some number of joint limits which we have to take it into the count. So if the obstacle break C space, C free into separate components, and as you can see in the diagram, Q0 and Q1 are not in the same connected component, then there is no collision free path. So it shows you that in the first frame you can see that there is a Q0 and Q1 which is not in the same frame, and then it got stuck in between the frame, and then it is showing you the collision. But in the second frame you can see that the point is far away from the obstacle, and it's connected towards each other, and and you can see that the motion from x0 and to x0, it's more smoother. So after that you can see that, let's take an example for the circular mobile robot. So as you can see, there is a circle and there is a configuration x and y. So we have to go from lower bottom left of the right hand triangle to towards the right hand point, and then goes up to the hypotenuse and towards the left of the top. So in the second diagram you can see that there's a pink line moved, and there's a black line dot, a black line um, um, broad. You can see that it's right across the centers where the robot is moving from edge to edge of the triangle. So from there you can see that it's moving very smooth and without colliding to any obstacles. And on the last and the foremost, you can see that the movement of the robot in the triangle and in the rectangle section, it got collision in between, which will which is a problem to solve. So as you can see, what is an R in the configuration space? It's a script pose the robot. So it basically gives you the momentum of the robot from one point to from the starting point to the final position. So as you can see that the representation of R in the configuration space would be something like, from you can see the yellow part is the robot. So it moves from one point and goes right across the whole box, the whole rectangle. So you can see the R configuration in the lower triangle, in which it mentioned in the purple lines that it's moving from one point to another right across the edges without um, any collision in between the obstacles. So from here, let's take an example. As you can see in this, um, there's a mention of the robot which is at the 0 0 position right now, and then it has to go from right across the whole triangle and then come back. So we have to figure out the number of our configurations where the robot is going to move. So as you can see from here, the robot is moving from 0 0 to 4 comma 2, where it will get the touched from the lower bottom of the rectangular section, and then it goes from there to right across 4 comma 4, where the momentum is going on, and in between there from 4 comma 4 to 7 comma 7 it moves 7 comma 2 it moves linearly, and then it goes from 7 comma 2 it goes to 8 comma 3, which is a translation movement, and we are not supposed to do the rotation movement in it. So we are going from 7 comma 2 to 8 comma 3 without the rotating of the robot. So as you can see, the our configuration is 4 comma 2 7 comma 3 7 comma 2 8 comma 3 8 comma 4 and then 4 comma 4, where the robot will be moving from x starting position to the ending position x comma 4 comma 4. So this is the end. This is the motion planning of the robot. Thank you.